Boldly going where no science show has gone before. The Naked Scientists.
This week, science from the land of kangaroos, koalas, bandicoots and the Square Kilometre Array. Hello, I'm Chris Smith and I've just touched down from a tour of Australia and I've brought back with me a sample of some of the colourful characters that I met along the way. And where better to begin a nationwide tour than with a ride around the universe.
My name is Carly Tillett. I work here at Horizon the Planetarium at SciTech in Perth, Western Australia. And every day we get to introduce people to the universe, which is a fantastic job.
Now, I'm going to make a confession to you, Carly. I've never been in a planetarium.
And I can't believe that.
So you're robbing me of my planetarium virginity. For people who, like me, have never set foot in something like this, can you paint a picture of where we are, what we're seeing, what's in front of us?
Okay, so you would have to imagine a really big 18-metre, like a dome screen. So rather than a flat television screen, this thing is like half a sphere. And you get to sit underneath it, and we project images of the night sky and beyond up onto this big, gigantic screen.
So basically, for the 150, 200 seats that are in here, there's a white screen above us. That is going to become a surrogate night sky that you can put stars on.
Not just a night sky, we can show the entire universe.
Should we do it?
Yeah, I think we should.
So how does it work? Because this looks like mission control. I'm looking at this computer screen, and to say there's a few things to click would be an understatement.
Yes, there are lots of things to click and press. Part of my job is to program within this software called Digital Sky by Skyscan, and I get to input 3D models and show really hardcore astronomical data sets. But usually, for a planetarium presentation, we start with the simple stuff, a sunset scene, just so people can get a little bit comfortable before we plunge them into darkness. And we can see the sun setting and the stars in the night sky, as they will be tonight in Perth at about 8 o'clock this evening.
So could you recreate the UK skyscape for me here?
Surely could.
So you can do pretty much what the night sky would look like from anywhere on Earth?
Yes. Do you want to go to South Pole?
Yeah, go on then. I've never been there either.
It's a day of discovery.
So how is this working? How does it know what to put where? Because I can just see millions of little dots of light appearing on what is a surrogate sky above me.
Indeed. Basically, we have 6 projectors that each project onto a little kind of pie slice of the dome. And there are 6 computers that run each of the 6 projectors, and then one that controls them all. And that's the screen that you're seeing right now. It's the main control kind of computer.
It's a lot of computing power, isn't it? But I guess that's needed.
Indeed, definitely, especially to achieve the resolution, so the ability to be able to see pictures that aren't pixelated and all horrible. So we can show a really, really nice image and people can get a really quite good idea of what's up there in the sky. So this is the South Pole at night time.
So how do people react to this? When you show them this, how do they react?
It depends on how old they are. Children tend to be very excited, especially when we do things like spinning. Adults think it's quite awesome and inspiring. Sometimes don't like the spinning so much, but I think there are many adults that might grumble, but we know they enjoy it.
Some people say it's quite disorientating because you end up gazing upwards, and because there's no reference point, because it's dark, you end up getting quite giddy.
That's true, and while it can make people feel giddy, it's also one of the most amazing points of having, especially a tilted dome like we have here, is that people can feel within the scene. So at the moment you're seeing an Earth on the dome, and I've actually pulled us up into space, and if I just rotate around, you can actually feel like you're in space looking back down on the Earth.
Wow, so how far back from... I should just explain, so we've now zoomed off of Earth's surface, we're out in orbit somewhere, so how far away from planet Earth? I can see this giant planet projected in front of me. How far out are we?
About 18,000 kilometres.
So that's not quite as far as, say, a satellite that would bounce geostationary images back for TV and stuff, is it?
No, they are about 36,500 kilometres out. I can actually show you.
Oh gosh, so now you're projecting all the junk, basically,
Yes.
that's orbiting the planet.
Yes, this is space junk, a wonderful trash in the sky, which sounds kind of funny at first, but it really isn't, especially if you're an astronaut on the International Space Station, which we can see here, it orbits around the Earth about 370 kilometres above the Earth. The astronauts on board sometimes have to move up into the Soyuz capsule just in case a piece of space junk crashes into the International Space Station, which is a little bit scary.
But looking at this picture, there are literally thousands of white dots representing debris up in space. How many objects are there up there, man-made objects in orbit now?
There are over 800 working satellites, but as for space junk, it's almost uncountable. There are so many chunks of space debris, from old satellites that are no longer working to paint flakes and nuts and bolts that have fallen off, and even some countries have decided to send missiles towards an old defunct satellite, turning into, 25 or 26,000 individual little pieces hurtling around the Earth at more than, 26,500 kilometres per hour. It's a bit of a mess up there.
Are we in a position where people are beginning to say, look, we're making a mess as well of the Earth's surface, also the Earth's orbit, and we're going to have to clean this up at some point? Is this actually harming astronomy?
Not so much astronomy, but certainly it puts a lot of satellites at risk. And satellites are not cheap. We're talking about billion-dollar instruments, whether they're for Earth observing or for our cable TV. Satellite TV even.
It'd be a long cable, wouldn't it?
It'd be a very long cable. Yeah, that was a bit of a mistake. So yeah, there are lots and lots of satellites up there, and there is a lot of work going into researching how we might be able to stabilise some of the orbits of some of the older satellites, but also how to basically clean up our act up there in space.
So could you also use this to begin to understand more about the relationships between objects in space and the Earth, other planets and so on?
Absolutely, and even next week I've been working on a production with an artist called Dave Carson, and he's been working with Janos Hanicki, who spends about 3 months per year on Christmas Island tracking Abbott's boobies and frigate birds, which are birds that travel these massive distances. So I've been able to visualise data from Janos's tracking to be able to show that these birds used to travel maybe just one day at a time to catch their fish feed, and now they're having to travel 2 or 3 days to get that same feed. So we can show not just astronomy, but of course other science, and I think it really gives people a great perspective when you can actually look from above at these kind of things.
Oh, so you can actually plot information on something like this relative to the Earth's surface and use the power of this kind of projection system to be... It's like doing a massive Google Maps mashup, but you've got the world's best projector, isn't it?
Pretty much. We've certainly got the best computer screen. What more could you ask for? 18 metres of domed goodness. It's a pretty cool place.
So not just for pretty planets. Carly Tillett's talking to me at the SciTech Planetarium in Perth. And that spinning that she mentioned is actually a vertiginous trick that she's developed to rotate the picture you're seeing several times a second, which makes you feel rather like a human bowling ball spiralling through space. So do take some anti-sickness pills before inviting her to show it to you. Now, from the depths of deep space to the depths of your stomach. And if you've ever been afflicted by an ulcer or gastritis, here's the man who won a Nobel Prize for discovering the bacterium Helicobacter pylori that's responsible.
Barry Marshall, here I am at QE2 Medical Centre in Perth. It began in about 1981. At that time, I suppose I was 30 years old, and I met up with Dr. Warren, who had seen these curved bacteria on stomach biopsies. He's a pathologist, you see. And so it was a curiosity for us to investigate this further. How come bacteria can live in the stomach, which is supposedly full of acid and kills bacteria? So nowadays we know that bacteria can live in hot springs, but that was pretty much new stuff in 1981. And so we set out to perhaps identify and culture these bacteria, and I went off to interview all the patients that had them on the biopsy to see what was wrong with these people.
What made you think there might be something in the clinical history that would be worth investigating? Why did you decide to follow that up? Because it would have been easy to just say, oh, there's some bacteria in the stomach, maybe we missed them before.
Well, they were new, so obviously there was no knowledge about them, so we had to exclude the possibility that they were causing a disease. And when we did interviews with people, we found that there were one or two symptoms that seemed to be connected in some way. Dr. Warren knew already that they caused inflammation in the stomach, which was gastritis. But the teaching was that everybody got gastritis if they lived long enough, and who knew what it was caused by, spicy food or smoking or alcohol, something, 100 different explanations. But according to his pathology results, you really had to have the bacteria to have gastritis. So we then set out to find, what about people who don't have the bacteria? Do they have white cells in the lining of the stomach? Do they have any symptoms? And we went off with open minds, just trying to find out what the patients would tell us. And we came back with nothing initially, because people could have indigestion or belching or dyspepsia or nothing or anemia, all kinds of weird things, or ulcers, but nothing came out in our pilot study. So we said, okay, let's do it properly now. We'll do a prospective study. We'll look at 100 patients. We'll take every single patient having the endoscopy down, so a very big mixture of people. It was done blinded, so you didn't know what was wrong with them, what the results were. And when we looked at the results, the ones with ulcers had the bacteria, far more commonly than just anybody else. So that was a significant result, and that was a year later that we had that result, and already we'd studied the literature, and it all fitted together all of a sudden. Hang on a minute, maybe ulcers are not caused by stress, maybe they're caused by a germ in the stomach. Nobody had ever thought of that, because supposedly you couldn't actually have bacteria in the stomach because the acid kills them. So once you say, well, that was wrong, all of a sudden it's wide open.
The question is, though, it's one thing to say there are bacteria in the stomach and there's an ulcer, but how do you resolve the question the bacteria are there because they've caused the ulcer, rather than the ulcer has made the stomach environment change in such a way that it now allows these bacteria to persist?
I'm getting deja vu, because that's exactly what people used to say who didn't believe us. And so we said we have to prove that these bacteria are harmful or harmless. And of course that is an experiment called Koch's postulates, where you have to infect an experimental animal with the bacteria. But sadly, we didn't have a successful experimental animal, so we had to then look for human volunteers. And Warren and I discussed this, and he couldn't be a volunteer because he'd already had Helicobacter, and I had treated him, so he would have been a bad choice, and I hadn't had them. So it fell upon me to do the experiment. So I did drink the bacteria, a few tablespoonfuls, not very much. And it didn't really, well, actually, it's not published yet, so I won't tell you what it tasted like. It wasn't too bad. So then I was just waiting to see what would happen. By then I knew that there were lots of people that didn't have ulcers, who had the bacteria. So I was there like, I suppose nothing will happen, because none of my ulcer patients can remember catching the bacteria, so probably they're not going to cause any problem. So I was quite surprised when about 5 days later I woke up and ran into the bathroom, started throwing up. And I was vomiting for about 3 days. Not a lot of vague symptoms, but nothing that you could really hang your hat on. And then after that I was okay. And the endoscopy was done, and sure enough I had millions of these bacteria, thousands of white cells all trying to eat the bacteria. So it was really a bacterial infection that I had in the stomach. So that answered this question. It said healthy people with nothing wrong with them can catch this bacteria and then get inflammation in the stomach called gastritis. So that was then the soil upon which an ulcer would form later in life. And so we connected the whole story up at that point.
So what is the bug actually doing, and why is the immune system not dealing with it?
Well, it's a bit like D-Day. All the ships are parked off shores out of range, firing at the coast. And so that Helicobacter is like that, living in the mucus, hammering away at the epithelial cells, making them a little bit leaky so that they leak iron and nutrients up to the bacteria. So that's the happy status for the bacteria. As soon as you get too many white cells migrating through the epithelium in the stomach, it's starting to develop holes in it. It becomes leaky, acid goes down, and you develop an ulcer. So that would be disadvantageous for the bacteria. They don't want to kill you because then they can't propagate. So a successful bacteria lives in sort of symbiosis. So what they want to do is keep the inflammation going, but not so vigorously that you die from a bleeding ulcer. So an ulcer is actually, the bacteria is a bit overzealous, if you like, in harming you. That doesn't want to do that. So it has toxins, and one of these toxins, called the VAC-A toxin, probably down-regulates the immune system. So as soon as you get too many holes in the mucosa, this stuff would be leaking into the lining of the stomach and inhibiting the proliferation of the white cells. So that's the kind of thing that it would be doing. So your immune system then gets a bit paralysed and doesn't actually become more vigorous as it would do. So you can imagine maybe 500,000 years ago, the first Helicobacter infects humans. It's too dangerous, and the poor old humans probably died from bleeding ulcers. However, one of the Helicobacters mutated and developed this immune suppression system and got the right balance, and now we all have Helicobacter all our lives, or we used to, but in the last 100 years it's decreased to about 25% of the population in most countries. So you can pick it up as a child, and it sits there controlling the immune system, regulating it for the rest of your life. And so it's a very mild irritation in the stomach, and most people don't know that they have it. 10% of people at some time in their life develop ulcers, and that is a major event because ulcers then come and go. So you put you in the high less acid level. And then if you have Helicobacter all your life, that irritation and inflammation attracts stem cells floating past, and these stem cells try to fix up the problem in the stomach, try to make it heal, and they're proliferating and they're subject to hits by carcinogens that you might eat. So you do get 1 or 2% chance of having stomach cancer if you live as long as a Japanese person, 80s or 90s.
Barry Marshall, the man who ate his own experiments to prove that the bacterium Helicobacter pylori can cause stomach inflammation, ulcers, and even cancer. And Barry also told me that he's now working on a way to produce tamed forms of that bug that can be used to deliver vaccines against other diseases like the flu.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientists with me, Chris Smith. And this week, I'm taking a look at some of the hot science that's happening across Australia. Embarrassingly for the average Aussie, as a nation, they're amongst the worst emitters of greenhouse gases on a per capita basis of any country in the world. So why aren't they making more use of all that lovely sunshine they enjoy? Lee Shepherd.
We're interested in generating alternative fuel as a substitute for fossil fuels. So we're focusing on splitting water to produce hydrogen from sunlight using various catalyst materials.
How are you doing it?
We're using a material based on titanium dioxide, which is a very common material. It's in a host of common things like white paint and sun cream and toothpaste. And it's a metal oxide. So there's metals and there's oxygens. If we change the ratio of those metals to oxygens, we change the properties. So we take our material, we put it in high temperature, various gas atmospheres, and we're able to sometimes suck oxygen out and sometimes impose oxygen in. And as a result, we have titanium dioxide that's a little bit tweaked, a little bit different than what you would get normally. And it has different properties as a result.
So you fabricate this structure, then you illuminate it in the presence of water, and it degrades water molecules and yields hydrogen and oxygen.
That's exactly right, yes.
So practically speaking, how does it actually work?
Okay, what happens is when the sun or any light source illuminates the titanium dioxide, some of that light, that's the high energy part of that light, forms electronic charge carriers, like electricity, inside the material. And once that happens, we drive essentially electrochemical water splitting. So it's like an old-fashioned beaker with 2 copper electrodes plugged into a power point somewhere and you split water. Same sort of experiment we're doing, except that one of those electrodes can't be copper. It has to be a material that's powered by the sun.
And that's the titanium dioxide?
That's right, yes.
So you make some electrons or a surplus of electricity in one of the electrodes, harvest that off and then use that to split the water?
Yeah, in simple terms, that's exactly right.
So this is a way of basically producing clean hydrogen?
Yes. One of the problems with hydrogen today is that it predominantly comes from natural gas. So while hydrogen in itself, if you had that in a car, you'd be driving along and only steam is coming out of the back, you can feel good about yourself, but that hydrogen's come from a dirty source. It's come from a carbon source. We want to break that link and we want to produce hydrogen in a way that's entirely free of carbon emission.
Can you do it in a way that's economical and also environmentally sustainable, though? How much hydrogen can you make?
This is the challenge. It all comes down to performance. And for us, this is early days. It's an important project. I think it has important consequence for the future as we all rely on energy. But it is early days, and it's about lifting performance, absorbing more sun and splitting more water. That's what it's all about.
How much can you make? In other words, how much sunlight do you need to make hydrogen that would be sufficient for me to run my car to get me to work?
Well, this is a question that comes back to efficiency, ultimately. And at the moment, efficiencies are very low. It's not practical at this stage to split water using sunlight to drive something like a car. It's too early in the technological development to do that sort of thing.
So what makes you think that titanium dioxide is the way to do it? There must be other materials that are better then.
The virtue of titanium dioxide is that it is highly corrosion resistant. There are a number of other materials that have better abilities to absorb sunlight, but of those materials, they're either extremely expensive or they don't last long in an aqueous environment. You need to start with an oxide, essentially. And like I said before, it's all about changing the properties of this material. You start off with something that's corrosion resistant and abundant and cheap, but it has its drawbacks, and that's what we are about addressing.
And so what would be the long-term goal of this? Would you have some kind of centralised system where you have big arrays of panels that would make enormous amounts of hydrogen, which you then distribute? Or could you see this even being practical on a domestic basis, where people make homemade hydrogen that then powers their home, powers their car and so on?
What I like to see it would be a situation where people can take a bit of control over their energy production as well as their energy consumption like we have now. Whether this is something that is favourable on a big scale, time will tell. This is just my personal preference at this stage.
Lee Shepherd. He's based at the University of Western Sydney. You may not have heard of a bilby, but believe me, these mini marsupials are extremely cute. But they're also an endangered species in Australia, alongside many of the country's other native fauna, largely owing to feral animals, like cats and foxes, that have been introduced from Europe. But now a major initiative called Project Eden, which is based in the Francois Peron National Park in Shark Bay, northwest Australia, has been set up to tackle the problem by returning a patch of the country to what it would have been like before rat and cat-bearing European settlers arrived on the scene.
I'm Brett Fitzgerald. I'm the District Manager for the Department of Environment and Conservation in Shark Bay District. The aims for Project Eden are to reconstruct the original native fauna on the Peron Peninsula within Shark Bay. So that's done through a combination of getting some information on what species were here originally, then managing the actual pressures that are on those species, the ones that are remaining, and the artificial pressures that possibly pushed some of the others to extinction.
And what were they?
The main pressure that we've seen on not only Peron Peninsula as across Australia is the introduction of feral predators. The feral cat, which has been around for longer than foxes, but in synchronisation with that, species such as rabbits, which have provided a prey source and a food source for the introduced predators, which lets them build up to numbers. And then what it appears to have happened is we then have a crash of those introduced prey species, such as rabbits, and then the predators are at such large numbers they move across to what are possibly remnant and smaller populations of native animals and push them towards extinction.
So why have you chosen this site to try this experiment, to try and make this happen?
Yeah, across a lot of Australia where we've seen native animals survive, native species survive, has been on an island environment because we haven't had the feral predators introduced. The difficulty with working on islands is simply access. They're remote and logistically they're difficult places to work on. Peron Peninsula inherently was a mainland island. It's 100,000 hectares, so it's 1,000 square kilometres, but there's only a narrow neck about 3.2 kilometres wide which connects that large peninsula to the mainland. So by fencing that off, controlling feral animals inside the enclosed area, we can limit the potential for reinvasion and I guess get the best value for money for the eradication programs.
What have you done in terms of getting rid of those nuisance animals that us Europeans brought here a couple of hundred years ago?
We've controlled the large herbivores, so species such as feral goats and sheep. And Peron, before it was purchased for conservation, was an operating sheep station, and goats were not really used commercially in those early days, but they were present here as well. So that's a combination of mustering, trapping and eradicating those species. They're large, they tend to come to water in summer, so they're relatively easy to control. Then we've had red foxes, which are a common species in Europe, but introduced to Australia. They tend to be relatively easy to control by a naturally occurring poison placed in a bait here. So the estimates were between 2,000 and 3,000 foxes on the Penrhyn Peninsula before control commenced. We have the occasional one that might sneak through the fence or sneak around the fence, but we're in the order of single figures of foxes on the peninsula. The fourth major species that we've been looking at controlling is the cats. And unfortunately, control of feral cats is an incredible challenge. They've got a great breeding capacity. They don't need to drink water. They are quite adaptable with the prey they select. So they're a difficult nut to crack in a sense as far as eradication goes. And they've proved a big challenge. As have rabbits. The rabbit population here tends to fluctuate with season. We have periodic outbreaks of natural diseases such as myxomatosis, which depletes the population, but rabbits have an incredible breeding capacity, and even when the numbers are suppressed, once we get some reasonable rainfall, they bounce back, and they're also an issue.
Brett Fitzgerald. And apart from just eradicating the feral animals to let the plants and native species recover, Project Eden also has a captive breeding programme to help kickstart the process. Colleen Sims.
Let me show you here one of the animals that we've been breeding. This is a bilby, or more correctly it's called a greater bilby. These guys used to be very common across Australia, around about 70% of the country. They are a marsupial and a burrowing marsupial. So one of the unusual things about many of the burrowing marsupials is they have a pouch that points backwards, so they don't fill them up with sand when they dig.
That could be a disadvantage, couldn't it? It's about the size of a rabbit, isn't it, this one?
That's
It's a small rabbit.
Yep. As you can see at the very long ears, one of the common names was the rabbit-eared bandicoot. The bilby is one of the bandicoot family. And they're actually omnivores rather than a herbivore like a rabbit. So they'll eat anything from seeds, root tubers, insects. They also have been known to eat mice and small geckos and things too, so they'll pretty much go anything that gives them a good feed. They have some fairly sharp teeth, obviously, considering the array of food they eat. The other thing that's a dead giveaway for their behaviour, I guess, is if you look at their forearms. They've got very strong, short forearms and very long claws for digging on the front feet. They can go along at a fairly good clip. I guess it's fairly similar to a rabbit gait, in fact, a sort of a half-hopping gait to start with, and once they get fast, they will actually really get running. They are nocturnal, so they live in burrows during the day, anything up to about 2 or 3 metres deep, so they can move a lot of sand, move it very fast. They actually were a fairly common food source for the Aboriginal people, and still are in some of the remote desert regions, but it takes a lot of effort for them to actually dig a bilby out of its burrow.
So given they can hide underground, why are they particularly vulnerable to things like cats and foxes then?
The reality is they probably are one of the less vulnerable. The fact that they actually do still exist and persist in Central Australia at this stage means they're doing a lot better than many of the other species we previously had here. That doesn't mean they're immune, and there's certainly ongoing concerns that they may still be slowly shrinking in numbers. Because they're nocturnal, because they are omnivores and move about the landscape depending on food sources, it's quite difficult to monitor them. Often you can return to an area where there was quite a thriving bilby colony, and several years later they aren't there anymore, and it does create problems to work out whether those animals, that population has actually gone extinct or whether it has moved somewhere. But there's certainly ongoing concerns that even though they were persisting in the desert areas, that population and the range may still be shrinking.
So when you want to breed an animal like this in captivity, what does that actually involve?
Obviously, it initially involves getting the original animals from the wild and setting up a program. We have a fairly intensive management program here to try and manage the distribution of the genetics through the breeding population. These guys are actually comparatively easy to breed. They've actually been partially adopted in Australia as a replacement for the Easter bunny. Obviously, the similarity in appearance makes them quite convenient for that, but also because they are actually quite a rapid breeder, so the fertility aspect is actually carried on. So we have an Easter bilby these days in Australia. We'll usually get anything up to 3 or 4 litters out of these guys in a season, in a year. So they'll produce usually a litter of 2, but anything from 1 to 3. And we will usually, based on some advice from the National Stud Book, that gives us an idea of the relationship of various bilbies we have in our colony. We'll pair a male and a female, and they may stay paired for most of their time here. We may get, once we've had 3 or 4 litters, we might decide we actually want to move pairs about and remanage the pairings and the genetic lines from that.
So when a baby pops out, it first of all goes into this backwards-facing pouch.
Mm-hmm.
How long does it spend in there?
The bilbies, as mentioned as a bandicoot, actually have a really rapid reproductive rate. Their gestation is only about 10 days. So, as with most marsupials, the fetus comes out very small and very underdeveloped, and they then spend around about anything from 65 to about 75 days in the pouch.
And are they sociable? Will they hang around with a family group, or do they go off on their own and act independently as soon as they get out the pouch?
They'll usually spread out and disappear. In fact, some may think this is a great idea we should do with our kids, but the bilbies, the females, actually will leave the burrow, the home burrow, to the kids. So she's the one who basically leaves them after around about 2 weeks after they come out of the pouch.
Colleen Sims, who's a vet and project officer with Project Eden. But apart from the important task of increasing the numbers of endangered species, there have also been some other surprising discoveries. Brett Fitzgerald again.
It's interesting to actually watch in the reintroductions. It's so much more than just putting back the small furry animals. When you actually look inside the breeding pens of the bilbies and when you look at areas where they've been reintroduced, these actual deeper diggings that they do, you can actually see the way that functions as part of the ecosystem. A lot of the seed that's distributed in Australia is airborne and wind-driven, and you'll actually see in these deeper holes that bilbies dig, the actual seed falling to the bottom of the hole, then having some dirt blow over the top of them. And so as far as driving the ecosystem, as far as plants germinating and plants getting a chance to survive, you really see the function the animals played as much as just their presence in general. Water penetration, when you look inside a bilby pen or around a bilby release area, you may have these shallower rabbit diggings, but the bilbies really turn the ground over. And when you think when we have a rainfall event after that, the capacity for rainfall penetration, water to actually soak into the soil rather than run off and disappear, is that much increased by the presence of these animals. So that's been a really interesting part of the project, is not just to see the animals back in the natural environment, but to actually see the ecosystem function they played.
Do you think it's been successful, though?
I think we've had some real successes. Some of the species, such as malleefowl, from a process of collecting eggs to actually hatching those eggs, to releasing those birds and then actually going out and finding active breeding mounds on the Penrhyn Peninsula. Some of those species, bilbies included, we've seen a real success, and it's essentially made Penrhyn a site where we can potentially take those animals bred here to other locations and really use this as a launching pad. It's been challenging, and feral cat control is a challenge, but as well as the effective control here, the other things we've learned is better techniques. So it's a learn as you go process with some of the species and some of the feral control. The techniques they've developed here and the things they've learned about cat behaviour have been able to be applied, not just in Australia, but in other parts around the world. So, yeah, I think we've had some real success with the species reintroduced here, and we've learned things that have been able to be applied in other places.
Brett Fitzgerald from Project Eden in Shark Bay, Western Australia.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists. I'm Chris Smith. Back into outer space now, and a project to see farther than we've ever seen before. Peter Quinn.
The world, 20 countries and radio astronomers in them, are trying to build the world's biggest radio telescope. Okay, it's called the Square Kilometre Array. It's a poor choice of name. It's not square and it's not a kilometre long. It's different. Okay, so if you look at a radio telescope, say like Parkes, the famous dish, as it was in the movie, right? So it's an eyeball, right? It's 1,000 square metres of metal dish which collects radio waves, focuses them into a point, and there it's turned from analogue to digital and makes images basically of the sky. That telescope is really good to look at the local universe, the universe immediately around us, the galaxies and clusters of galaxies we can see on pictures that most telescopes take. The biggest radio telescope we have, which is about 10,000 square metres, so about 10 times the collecting area of the Parkes dish, pushes us out to kind of the very edge of detectability of galaxies. And if you were to draw a ruler, okay, out into the universe from here where we are today, we'll call that 0 on the ruler. Where on the ruler could you get to with our biggest radio telescope? The answer is 1 unit out there. We'll call it, the farthest we can see right now is 1. So where would we really like to be able to see to into the history of the universe? And the answer on that scale from 0 to 1. We would like to be looking at 10, effectively 10 times further out into the universe than we can see at the moment. So what's out there at 10 times further? 10 times further, it puts us in a point in the history of the universe when the very first objects formed. The universe began with a Big Bang, we know that, and it was a very hot and sort of gaseous place. And as the universe expanded, it cooled and starts to form objects. And those objects were the seeds of every other object that's ever been, the seeds of stars, the seeds of galaxies and planets and what have you. So that process of the universe cooling and the very first objects being formed happened at number 10 on this rule that we've just talked about. So we can only get to one unit on the rule. We need to get to the 10. So that 10 point is sufficiently far away, sufficiently far back in time. It's effectively 10 times further than what we can currently see. And why do we want to get there is if we can see the beginning of the story, then we know how it all turns out. It's like having a novel with the first few chapters ripped out, okay? The universe is a bit like that for us. We know the end of the story. We know we're here and we can see things around us. But as you look out into the universe, you're looking back in time. So you're looking back to the beginning of the story. And so we're trying to fill in those blanks. We don't know how this story began. We don't know what the first objects were, what they looked like, whether they were monster black holes or monster stars or little tiny galaxies, or how did this process begin, and then how did it unravel, how did it actually build up as time went by. So it's very simple. If you want to see 10 times further away, how much bigger telescope do you need? Unfortunately, it's 10 times 10. 10 squared because it goes like the area. So 10 squared times, 100 times bigger than the biggest thing we have right now. The biggest thing we have right now, as I said, is 10,000 square metres, the big telescope in the US. So 10,000 times 100 is a million. A million square metres equals a square kilometre. So a square kilometre is exactly how much metal collecting radio waves we would need to amass together to be able to detect this incredibly faint signal from the very beginning of the universe.
And practically speaking, what's it going to take to do that? Because no one's going to build a dish like that. So how are you going to do this?
It's basically dishes. So the way we do this in radio astronomy is you make individual dishes. Each of those dishes could be 10 or 12 or 15 metres across. And an ensemble of those dishes will then make up a square kilometre's worth of collecting area. So if you want, say, a square kilometre and you made it out of 15 metre diameter dishes, you'd need about 3,000 of them, okay? So these 3,000 dishes have to be all built, all equipped with radio receivers, and all that information has to be gathered and turned into images of the sky, effectively. Those dishes also have to be spread out. You can't just stick them all together inside a little corral. You've got to basically spread them out. And in fact, the further you spread them out, the better your picture. It turns out that, in fact, the larger the separation of the dishes, the more resolution, the finer the picture, the finer the detail that you can actually make in your picture. So, in fact, we would like to spread the 3,000 dishes across a distance something of the order of 3,000 kilometres. Okay? So not only is it a large number of dishes, it's also a very large machine for doing science. The world's, in fact, largest kind of scientific machine almost, that it's 3,000 kilometres worth of stuff all connected together with fibre optics doing fantastic science.
So the major remit is a big country with a lot of open space that you can pack in 3,000 dishes. So Australia's perfect.
So it just so happens Australia happens to be 3,000 kilometres across just by pure accident. But, I mean, yes, you need a lot of flat, wide open space to be able to build this thing. You also need something else which is incredibly important. You need no people. Okay, you need to have silence on the radio spectrum front. The reason is obvious, because the signal you're looking for is coming from the very edge of the universe. It's very, very faint. And everybody makes radio noise. Mobile phones, microwave ovens, electric fences, trucks, buses, cars, whatever it happens to be. Anything that has a spark plug or any kind of electrical connections makes radio noise. But we want to be able to, particularly, as I said, be in isolated regions. Now, it just so happens that this western part of Australia, we have, for example, there's one place, it's called the Shire of Murchison, which is in the middle of Western Australia. It's a region basically the same size as the Netherlands, so a country-sized shire. Its habitation is listed formally as no more than 120. So that means you have population densities of around about 1 milliperson per square kilometre. A milliperson is like a big toe or two, right? So that's the kind of population density you need, around about 10 to the minus 3 people per square kilometre. In Europe, you have about 10 to the plus 3 people per square kilometre, so 1 million times less dense than Europe.
Okay, so we've got the ideal geography, but what about the data? How much data is each dish going to generate, and what sort of computing power do you need to gather that data and then assemble it into a meaningful picture?
That's actually one of the most ambitious and challenging aspects of this telescope. Just to give you some for instances, okay? Every year, everybody on the Earth generates data. And how much data do they generate? Well, every year the Earth kind of generates around about what's called an exabyte. So an exabyte of data is 1 and 18 zeros, a billion bytes of information. The SKA generates that amount of data in a day. Okay, so we're talking about something which outperforms the entire planet in terms of data generation. The other two sound bites I like to give about SKA data is that in 2020, when this telescope could be operational, the data traffic inside the telescope, just inside the telescope systems, will equal to the entire internet traffic in 2020. So take today's internet traffic, expand it up to 2020, the telescope will generate the same amount of data. And finally, the computer system itself. The computer system we need to run the SKA and transform all that data hopefully into knowledge will be the world's largest computer system, not today, but in 2020. So it's an incredible driver for the whole communications and information industry, and they're actually very interested in this project exactly for that reason.
And how much is it going to cost?
Cost is an important question too, and as scientists, we have to be very careful of that. And I think in this decade in particular, we have to be very careful of the way we spend public monies and actually cost the projects. We believe at the moment it'll be approximately 1.5 billion euros to build it, and something in the 1 to 200 million euros a year to actually operate. So that's the kind of costings we're working with right now.
So that's LHC, Large Hadron Collider level of funding, isn't it? So it's a lot. But it's not a massive amount when you look at the kind of impact it could make on scientific knowledge.
We believe that the impact of this project will be, I think earth-shattering is probably a good word, but bear in mind the following things have already happened. I mean, LHC as a project from CERN during the process of building that project invented the World Wide Web. Radio astronomy, even just in building the precursors, building the initial technology for the SKA, invented the standard which now defines Wi-Fi. So everybody that uses Wi-Fi in the world, that standard came from radio astronomy. So I think the commercial returns or the potential technological returns will be enormous. Scientifically, this is a project which is truly unparalleled, I think. This is a project which has not happened before. If you take Galileo's telescope, and you ask, how big a step was that for mankind? To go from the naked eye to Galileo's telescope, that was about a factor of order 10 times better than your naked eye. If we look at the impact and the step that SKA will make, it's a factor of 10,000. Now, that's 1,000 times bigger discovery potential step than any subject has made before in the physical sciences, right? So this is it's almost inconceivable what that means, right? I mean, given what we've done in building LHC and building other big experiments and how much advancement we've had, this is an incredible step forward. And it's not so much for the things that we think we will find, but for the things we don't know we'll find.
Peter Quinn, he's the director of the National Centre for Radio Astronomy Research in Perth, Western Australia. What have bees and gladiators got in common? Well, Boris Baer has been looking at their breeding habits, and it turns out the bee sperm actually fight it out amongst themselves to determine who's going to father the next generation.
Reproduction in honeybees starts very often when the colony gets fed up with the queen and they execute her, chuck her into bits and pieces and throw her out of the colony. And they then use the last eggs which she has laid before, and they start to breed new virgin queens. And when they hatch, they are normally separated for a while until everybody has hatched, and then they start to fight against each other until one or very few are left. And these queens then leave the colony for what we call a mating flight, and they go high up in the air, they release a pheromone, a substance that attracts males. And the males are coming in large numbers. The ratio between virgin queens and males is really extraordinary. In honeybees, about 16,000 males and one female. And they all queue up behind her, forming what we call a comet. So they basically queue up for copulations. And the female then kind of copulates with about 200 of them, or up to 200 of them. She kind of basically just collects ejaculates. She goes back into the colony and then she sorts these ejaculates out, but only very few, about 5% of the sperm that she accumulates during her mating flight will ultimately be stored.
So does she then use that sperm that she selects for the rest of her life? Because queens can live a long time, can't they? Years.
Yes, in honeybees they can live up to 7 years. In other social insects which we work with, they can live for decades. So we know that, for example, the ants, which we use for comparative studies, they can live for about 20 years. And they only mate very early in their life. Once they have laid the first egg, once they have initiated a new colony, they will never go out and mate again. And this has very dramatic consequences on the female because they have to store immense amounts of sperm, millions and millions. They have to keep it alive for all that time, and they have to use it very prudently throughout their lives to fertilize eggs. And that's quite fascinating. How can queens do this so efficiently?
So are you any closer to understanding then how they sort out this sperm? How do they decide of all these hundreds of matings, I want that sperm and I'm going to use it in whatever order, I'm going to flick out that sperm, I don't want that? How do they do that?
I think we start to get first insights into this. The male does not only transfer sperm to the female, the male also transfers a secretion, which we call seminal fluid or seminal plasma. And that seminal fluid consists of proteins. And when we looked at these proteins, we saw that they could be involved in little warfares between the ejaculates, but also between the males and the females. And we tested that in honeybees, and what we actually find is that some of these proteins seem to be able to recognize non-owned sperm and kill that sperm off within the female sexual tract. In the ants, where we kind of replicated that work, we could also kind of study the female side on this, and in these ants we found that the female secretions can actually cancel out that little warfare. How you can imagine this happens is that you have a picture in front of you of a gladiator in an arena. So the ejaculates then enter that arena, which is provided by the female. It's a sexual tract, and they fight against each other. We think the weaponry which they use are these proteins. And then you have losers, you have winners. But up there, the spectators, they will be the females, and they make, like in the old Roman, they make this really famous sign, thumbs up or thumbs down. So they ultimately decide who will kind of win, who will father offspring, and who will be chucked out.
And do we understand what the nature of that biological warfare is, what those proteins are doing, and how they're recognising, this is my sperm, that's a competing sperm, you're dead, my ones are going to survive?
That's actually what we have just started working on. We don't know yet what the specific proteins are or what the recognition process is. What we tried from our list to do is to kind of identify those proteins that are there, to then kind of test them specifically, whether they are responsible for that effect or not. And initially it sounds a bit kind of weird that like a liquid can recognize own from non-own, or a simple cell like sperm cell would be able to do this. But there were like a couple of studies that have been published over the recent months actually that all indicate that is actually something that should be there. There was a similar study that was performed in mice a couple of weeks ago where it was found that sperm in mice is also able to recognize owned sperm from non-owned sperm. So they basically align themselves, they kind of cluster together, but only those from the same male will form that alignment.
And understanding how this works, presumably this is going to inform better bee conservation and bee breeding strategies.
Yes, that's one of the ideas which we have, that deeper knowledge about bee breeding, bee reproduction will help also the bee industry to kind of breed better bees and to kind of ship semen samples around for artificial insemination programs. And we have like an artificial insemination lab here, so we're actually involved in breeding of more bees or bees of better quality.
So you're effectively creating a bee sperm bank?
Yes, to a certain degree. The advantage of the bee sperm is that you can keep it in a glass vial for a very long time. It survives for a couple of months without help and at room temperature. So if you, for example, you need a lineage which has an increased tolerance or resistance against the parasite, and that's at the moment a big issue, then you can, instead of importing bees, which is always risky, you can import semen. For some of the more kind of dangerous diseases that travel around the world in the bees, like the Varroa mite or the hive beetle, we know that's not present in semen. So we have a lower risk that we import something which we don't want to have here.
Bee biologist Boris Baer. He's from the University of Western Australia. And finally, we couldn't talk about Australia without talking about sharks, which thrive in the country's coastal waters. But one man I met in South Australia is concerned that the bait, or burley, used by tourist and cage dive boats to attract sharks for visitors to look at, could have some serious impacts on sharks' behaviour. Charlie Huveniers.
So we're looking at the impact of burling being the provision of bait in the water to attract the sharks so that people can undertake cage diving with white sharks, for example. And we're trying to look at how that burling might impact the behavior of white sharks. And previous studies have shown that whereas people previously thought the sharks would be conditioned to the burley, the opposite is actually happening, where we've got a level of habituation. So what I mean by that is instead of the sharks being attracted by the boat because of the burley, the sharks get used to the burley and basically don't react to the burley as much as they did previously. So if you've got a shark that arrives in an area on the first day of burley, that shark might be attracted to the boat and come around the boat and be able to be seen by the tourist. After a few days, we know the shark is still in that area through some of the tagging that we do, but it doesn't come close to the boat anymore. And that might be due to that habituation and the fact that even though there is burley in the water, there is no rewards because the sharks are not being fed by the bait. The bait is being removed on time.
It's a bit like me being attracted by the smell of coffee because I love coffee, so I flock to wherever the smell is coming from. Don't get a coffee. Therefore, in future I might ignore the smell of coffee.
Exactly, and there's many other examples we can also be using, but that's a good example.
And obviously, if you start to impact on the behaviour and preferences of a shark like that, it could have impacts, presumably, on its physiology, on its health.
It can have a wide range of impact, and it can potentially change some of the behaviour of the sharks, which we have to be careful of. It is a relatively large industry here in South Australia, but also around the world. There's the cage diving operation happening in South Africa, but also of Guadeloupe as well, and so it has implication internationally. And we're just trying to ensure that this kind of operation doesn't impact on the shark, but also that the tourist can enjoy this interaction with the wild shark as well. So the more we learn about the sharks, the more we can ensure that this operation is managed sustainably.
So is there a better way of doing it? Is there a way of attracting the sharks and rewarding them so that they're not being harmed in this way, or are you just trying to understand whether we are harming them and therefore whether we need to do things differently?
At the moment, we're trying to understand if we are harming them, but basically the sharks aren't supposed to be fed during cage diving operation. It's only the smell that would attract the shark to the area. So we're trying to ensure that this activity doesn't really impact on the shark.
Is there any evidence that it does?
I guess so far we don't really know, and that's the exciting thing about it, is that we're looking at something that we don't fully understand yet. I guess the important thing is that we know that the sharks would be there for a reason, but does the burling impact on the reason they're there for? And that's why we want to make sure that we're not changing the reason why they're there for, and the sharks still do what they're supposed to be doing while they're there, because they are there for a reason, which we don't fully understand. We just don't want to change that.
And how are you trying to explore that?
We're using a variety of techniques, and it's mostly related to acoustic telemetry. And acoustic telemetry uses a combination of receivers and tags, which you can put on a shark either internally or externally, and it gives us a finer scale movement and, I guess, residence time, which is the amount of time a shark spends in one area. I've got one of the tags here if you want to have a look at it.
Sure, go on.
So this is one of the acoustic tags. There's two different types of acoustic tags, what we call coded tags and continuous tags. This one is a continuous tag, so every second a pulse is being sent that is being received by the receivers, by the listening stations, and which then give us the location of where the shark is.
They're not very heavy, it's quite light. It's 6 inches long with a sort of slightly bulbous end. I presume there's a battery in there, and then there's the thing that produces the signal that you're then able to pick up.
So that bulbous end is actually just a float, so that when we insert it in the shark, it doesn't rub on the skin of the shark and just stays floating on top of it. And this is actually the tag here that has a battery life for these type of tags of about 40 days, but the coda tags that send a pulse less often will have a battery life of up to 10 years. So we can get information about the movement of sharks for up to 10 years, which is really interesting.
And how do you stick it on?
We just use a modified end of a spear, and we just simply, as a shark swim by the boat, we just insert it next to the dorsal fin of the shark.
So it goes under the skin?
That's right. It goes in the muscle. This anchor barb here just goes underneath the skin, and the tag itself actually floats just next to the skin of the shark.
No harm to the shark?
Nothing, especially in comparison to some of the mating that the sharks have, where the male will bite the female quite hard. So this is pretty much nothing compared to that.
That sounds like quite an interesting love life. So where do you record the acoustic telemetry points from? Have you got listening posts out at sea, and you're therefore resolving trigonometrically where the sharks are in any area in real time, so you can keep a sort of a 24-hour log, if you like, of a shark in that area?
That's exactly right. We've got two different systems, and one of them is what we call a VRAP, which is a Vemco Radio Acoustic Positioning System, bit of a mouthful. And what it does is got three receivers that calculates the position of the sharks using the difference of the time of arrival. So basically like triangulation. And the accuracy of that system is amazing. It gives us an accuracy of about a meter. So we will know within a meter where the shark is, and basically how it interacts with the different boats during the cage diving. So you can look at the time partitioning, which is the amount of time the shark spends next to each of the boats, to see how the burling changes the behavior of the shark. Does the shark spend its entire time next to one boat, or does it share its time between the two boats? So that if you want to add more boats, will the shark just spend the entire time with one of the 5 boats in one area, in which case the other boats might start trying to burley more and more to attract that one shark, but because you've got some habituation happening, the shark is going to be less and less responsive to that burling, so he's going to stay to that one boat, so the other boat's going to be even more burly, and you've got this kind of feedback and this escalating effect that might have large ramification and consequences for the sharks.
Any surprises emerging yet, or is this early days?
It's early days at the moment, and actually I'm quite excited. We've tagged a few sharks, and in a couple of days I'm going back there to download the data. So I'm really excited to try to find out what we've found so far, and hopefully it will provide us with good data and good results to be able to talk about.
Charlie Huveniers, he's from Flinders University in Adelaide. That's it for this week. The Naked Scientists are returning next time with a brand new series, and we'll be kicking off with a look at your science questions. So send them in now. The email address, as ever, chris@thenakedscientist.com. For the meantime, my name's Chris Smith. Thank you very much for listening, and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.